Hello, today we are going to finish section 3 of magnetic induction with lesson 16 of applying what we have learned. Today we have Amanda very happy, she's singing and she's glued to her microphone, and that makes it so everyone can hear her everywhere. In today's lesson, we are going to see how this device works, an electrodynamic microphone. And for that, we are going to see first the key parts that the electrodynamic microphone has. In the capsule, it has a diaphragm, and attached to it a coil. It has also got a stationary magnet that goes through the coil. But on what physical principle is based on the operation of this microphone? Well, it is based on the law of induction, that is the Faraday-Lenz law, which we already studied in previous lessons. Remember that Faraday said that the electromotive force induced in a closed circuit is directly proportional to the speed with which time changes the magnetic flux passing through any surface with the circuit as an edge. Lenz further stated that these induced voltages have a direction such that they oppose the variation of the magnetic flux that produces them. This is the expression of these two laws. The electromotive force is equal to minus the derivative of the magnetic flux with respect to time. But in this scheme of the microphone, where is that magnetic flux? Where is that time variation, the electromotive force? Well, the magnetic flux is the one being produced by the magnet. The magnet is producing field lines that cross the coil, producing, therefore, flux through it. Where is the time variation? Well, when the acoustic signal arrives, there is a mechanical wave that is able to move the diaphragm. That moves at the same time with the coil, and it is this displacement of the coil what produces variation in the magnetic flux, inducing voltage at the terminals of the coil. This circuit closes, producing an electric current that goes to the amplifier and from there to the loudspeaker that allows us to hear the sound. Let's see and identify all these elements that we have seen in the scheme in photographs of a real microphone. If one disassembles the microphone capsule, one will find this piece in which we see it has a magnet in the center. Then around we see that there are some copper-colored coils that correspond to the coil, and that transparent plastic that shines is the diaphragm. I also wanted to mention that the scheme of the microphone is exactly the same as the one we saw in a previous lesson in which we explained the ins and outs of a loudspeaker. Notice that the diaphragm would play the role of the membrane. We see the two coils and we see that there is a permanent magnet that goes through them. In the case of the loudspeaker, the signal we wanted to hear was introduced into this coil. That current, as it was immersed in the magnetic field created by the permanent magnet, was being affected by a force that moved the coil, and at the same time, it moved the membrane as well. This movement of the membrane displaced the air particles in front of it and produced the acoustic signal, the mechanical wave, which propagates through space. In the case of the microphone, when the acoustic signal reaches the microphone, that mechanical wave is able to move the diaphragm, which moves in unison with the coil and produces magnetic flux variation that causes the magnet. When this variation of magnetic flux occurs, the coil terminals are induced, the induced voltage that Faraday told us about. And just so you get to see that the scheme of the loudspeaker and the microphone are very similar, we are going to see an assembly in which we use a loudspeaker as a microphone. What we have done is to connect the loudspeaker, it is going to be the active loudspeaker, to a function generator that provides us with an alternating signal. That we also visualized it in channel 1 of the oscilloscope. Whenever the active speaker is running, we will put on top of this speaker, which is a passive speaker, whose signal we are going to record in channel 2 of the oscilloscope, and we'll see how the speaker picks up the signal acting as a microphone. Okay, and that's what we can notice in this video. You see that when we bring the passive speaker closer, it boosts the signal. It may seem that the signal captured by the passive speaker is greater than the main signal, than the original, but that is not the case. We have to observe the numbers here. Channel 1, which is the original signal, is represented at 5 volts per division, while channel 2, which is the signal perceived by the passive loudspeaker, is represented at 1 volt per division. What we can also observe on the oscilloscope is that the frequency of the two signals is exactly the same. They do match. Okay, there may be some offset due to the displacement though. And that's all. I hope you enjoyed the video and the course. See you all next time.